All right, let's jump right in and explore the fascinating world of quantum cryptography. We're talking about a realm where physics meets espionage. Think about all the sensitive information that needs to be protected online. Your online banking, top secret government communications, everything relies on encryption these days, right?
Absolutely.
But there's a fundamental challenge here. How do you make sure those secret keys, the ones that unlock the encrypted messages, stay truly secret? Especially in a world where it feels like anyone could be listening online. And this is where things get really interesting, because the mind-bending power of quantum mechanics might just hold the answer.
It's true. Quantum cryptography really changes the game when it comes to security. We're not just talking about building stronger mathematical walls here. It's about leveraging the very laws of physics to protect information.
Okay, so let's break this down for our listeners who might be thinking, hold on, what exactly is quantum cryptography?
Well, at its heart, quantum cryptography utilizes the principles of quantum mechanics. You know, those rules that govern the behavior of particles at the atomic and subatomic level. It's a whole different ballgame compared to classical cryptography. Because instead of relying on complex mathematical problems, quantum cryptography uses quantum phenomena, things like superposition and entanglement, to create codes that are theoretically unbreakable. And even better, to detect anyone trying to eavesdrop on our secrets.
So it's like we're using the quirks of the quantum world to outsmart the spies. I'm already hooked.
Oh.
But before we dive too deep, let's take a step back and compare this with how things work today with classical cryptography. I think our trusty friends Alice and Bob can help us illustrate this, don't you think?
Of course, they're always up for the task. So in classical cryptography, let's imagine Alice wants to send a secret message to Bob. She'll use what's called a public key to encrypt her message, which you can think of like a digital lock. Now, this lock is available for anyone to see, but only Bob has the corresponding private key. That's the only key that can actually decrypt the message and unlock the secret. One of the most common examples of this is RSA encryption, which is a cornerstone of internet security today. And it's considered secure because, for classical computers, it's incredibly difficult to factor the large numbers used to generate these keys.
Right, it's like a super complex math puzzle that would take a classical computer forever to solve. But now we've got these quantum computers emerging on the horizon. And I have a feeling they're not intimidated by big numbers, are they?
You're absolutely right. Quantum computers have the potential to crack these codes exponentially faster. That's because they exploit quantum phenomena, giving them a significant advantage. And that's what makes them a real threat to our current encryption methods.
That sounds a little alarming. But this is where quantum cryptography comes in as a potential solution, right?
Exactly. And one of the most promising areas within quantum cryptography is quantum key distribution, or QKD. It's all about using quantum mechanics to create and share secret keys between two parties, like our friends Alice and Bob. And the best part is, it guarantees that no one else can intercept the key without being detected.
So instead of relying on complex math problems that a quantum computer could eventually crack, we're using the very nature of quantum mechanics to protect the key itself. It's brilliant. Can you walk us through how this actually works in practice?
Absolutely. Let's take a look at one of the earliest and most studied QKD protocols, called BB84. In this protocol, Alice wants to send a secret key to Bob, and they'll use the polarization of single photons to represent the bits of the key.
I'm picturing these tiny photons spinning like tops, each carrying a secret code. So how do they ensure no one can intercept these spinning messengers?
Well, here's where the ingenuity of BB84 comes in. Alice randomly sends photons with specific polarizations to Bob, but here's the catch. Bob randomly chooses a filter to measure the polarization of each incoming photon. Sometimes his filter will match Alice's choice, and sometimes it won't.
So there's this element of randomness built right into the system. I think I'm starting to see where this is going.
Exactly. The crucial part is that after the transmission, Alice and Bob publicly share information about which filters they used for each measurement. But, and this is key, they don't reveal the actual polarization they measured.
So they're being transparent about the method, but not the result. Why is that so important?
Well, because if their filters happen to match for a specific photon, their measurements will be guaranteed to be the same. That's thanks to the laws of quantum mechanics. And these matching measurements become the bits of their secret key. Now, if their filters didn't match, they simply discard those results.
So it's a process of elimination, where only the perfectly aligned measurements make it into the final key. That's really clever. But what about eavesdropping? Let's say our notorious eavesdropper, Eve, tries to intercept those photons mid-flight. Can she get away with it?
Not a chance. And that's where the beauty of quantum mechanics really shines through. You see, in the quantum world, the act of measuring something actually affects the thing you're measuring.
So if Eve tries to peek at those photons, she's going to leave a trace.
Exactly. She has to guess which filter to use, and if she guesses wrong, it disrupts the photon's polarization. It's like setting off an alarm.
Ah, so it's like those photons have a built-in security system. Tamper with them and they'll scream. But how would Alice and Bob actually know that Eve has been snooping around?
That's the clever part. Alice and Bob compare a subset of their key bits, specifically the ones where their filters matched. Any discrepancies they find in those measurements are a dead giveaway that someone's been trying to eavesdrop.
It's like Eve can't help but leave a trail of quantum breadcrumbs. I'm starting to understand why people are so excited about the potential of quantum cryptography. This is amazing stuff.
It is remarkable, and BB-84 is just one example of how we can use the strangeness of the quantum world for secure communication. There's a whole family of quantum key distribution methods out there.
Okay, before we get lost in the sea of acronyms, let's step back and make sure everyone's on the same page. We've been talking about quantum cryptography, but I know there's also something called quantum-safe cryptography. What's the difference?
That's an important distinction. Quantum cryptography, like 2KD, uses quantum mechanics directly for security. Quantum-safe cryptography, on the other hand, is more like a preventative measure.
So it's like reinforcing our existing defenses, making them strong enough to withstand any attack, whether it's from a classical computer or a quantum computer in the future.
Exactly. While quantum cryptography harnesses the power of the quantum realm, quantum-safe cryptography focuses on strengthening our classical approaches. It's like having multiple lines of defense.
Okay, so two different approaches, both aimed at securing our information in this quantum age. But let's get back to quantum cryptography for a moment. You mentioned that BB-84 was just one example. What other fascinating protocols are out there?
One that stands out is Eckert's protocol. This one ingeniously uses the concept of entanglement to establish a secure key.
Entanglement. Ah, that's the one that even Einstein was puzzled by spooky action at a distance. Two particles linked in such a way that measuring one instantly affects the other, even if they're miles apart, right?
That's the one. It's like they have the secret connection. In Eckert's protocol, a source emits pairs of entangled photons, sending one to Alice and one to Bob. Each of them measures their photon, choosing randomly from a set of measurement settings.
So far, it sounds similar to BB-84, but with this added layer of entanglement. How does this spooky connection guarantee security?
Well, the brilliance of Eckert's protocol is that it leverages something called Bell's inequalities. These are mathematical constraints that govern the behavior of entangled particles.
So it's like a mathematical test for entanglement.
Exactly. After their measurements, Alice and Bob publicly compare a subset of their results. If those results violate Bell's inequalities, it's proof that their photons were truly entangled.
Okay, so it's like a mathematical fingerprint that confirms the presence of entanglement and therefore security.
Precisely. If the results don't violate these inequalities, it means someone, perhaps Eve, has tampered with the system. Because only genuine entanglement, this unbreakable link between particles, can produce results that defy those Bell's inequalities.
So entanglement itself acts as a security guarantee. It's incredible how we can use these strange quantum phenomena to our advantage. What other quantum cryptography gems are out there?
Another intriguing area is quantum secret sharing. This takes the idea of splitting a secret to a whole new level. Imagine Alice wants to share a secret key with Bob and Charlie, but she wants to make sure both of them are needed to unlock it.
So it's like a two-person authentication system, but powered by quantum mechanics. Tell me more.
In quantum secret sharing, Alice encodes the key information onto a set of entangled particles. She then sends some of these particles to Bob and the rest to Charlie. Neither of them can unlock the full key alone because they only have part of the entangled puzzle.
So it's like giving them each a piece of a treasure map. Only by combining their pieces can they find the treasure.
Exactly. And when Bob and Charlie want to reconstruct the key, they bring their particles together and perform a special joint measurement. This collaborative measurement allows them to extract the full key information that Alice initially encoded.
So it's like the key is woven into the fabric of their shared entanglement. It only reveals itself when all the authorized parties come together. Such an elegant blend of quantum mechanics and cryptography.
It is quite elegant.
What other quantum cryptography wonders are being developed in labs?
One final area worth mentioning is quantum-secure direct communication. This is a field that's still in its early stages, but it aims to allow Alice and Bob to exchange messages directly, with security guaranteed by quantum mechanics, without even needing a pre-shared key.
Wait, secure communication without even needing to exchange a key. That sounds almost impossible. How could that even work?
It's a very ambitious goal, and the methods are quite complex, but imagine this. Alice encodes her message onto a sequence of qubits, the quantum bits of information, and sends them to Bob. But instead of sending those qubits directly, she uses a technique called quantum teleportation to transfer the quantum state of her qubits onto Bob's qubits.
Quantum teleportation. That sounds like something straight out of Star Trek.
It might sound like science fiction, but it's a real phenomenon, and it's been experimentally demonstrated. The key is that the message itself never actually travels through the channel. Only the quantum state is teleported.
So if Eve is trying to intercept those qubits, she'll find nothing useful because the message isn't physically there. But how does Bob actually get the message if it's not being sent?
Bob, who has entangled counterparts to Alice's qubits, can reconstruct the message by performing a specific measurement on his qubits. It's like sending a set of instructions, a blueprint, that allows Bob to recreate the message using his own materials.
It's like a quantum magic trick. Secure communication without ever having to exchange a key that's truly groundbreaking.
Yeah, it's really mind-blowing how quantum mechanics is poised to revolutionize not just computing, but also cryptography itself. And we've only just scratched the surface here. There's a whole universe of quantum cryptography protocols out there being explored. It's a rapidly evolving field with seemingly endless possibilities.
It sounds like we're on the cusp of a quantum cryptography revolution. But I imagine there are still some challenges ahead, like with any emerging technology, right?
Of course, that's always the case. While the theoretical security of quantum cryptography is remarkable, real-world implementations still face practical hurdles.
Yeah, I can imagine that translating these complex quantum concepts into real-world applications is no easy task. What kind of challenges are researchers currently facing?
Well, one of the main challenges lies in the physical implementation of these protocols. For example, QKD relies on transmitting single photons reliably over long distances, and that's not a trivial feat. Photons can get lost during transmission, especially over fiber optic cables, and their delicate quantum states can be easily disrupted, introducing errors.
So it's a battle against distance and fidelity. It's like trying to send a whisper across a crowded room where the message can easily get lost or garbled along the way. What other hurdles are there in real-world implementation?
Another major challenge is the development of reliable and cost-effective quantum hardware. The specialized equipment needed to create, manipulate, and measure these quantum states, like single photon sources and detectors, is currently very expensive. So wider adoption of quantum cryptography really hinges on advances in quantum technology that make it more practical and accessible.
So it's a bit like the early days of computers, when they were bulky, expensive, and not very user-friendly. But just like we've seen with other technologies, as things progress, they tend to miniaturize, become more efficient, and more affordable. Speaking of security, even with these quantum safeguards in place, are there any potential vulnerabilities we should be aware of?
That's a great question, and you're right, we always need to be thinking about potential weaknesses. While the underlying principles of quantum cryptography are incredibly secure, implementations can still be vulnerable to something called side-channel attacks.
Side-channel attacks. Those sound interesting. What are those exactly?
Well, instead of directly attacking the quantum cryptography protocol itself, these attacks target weaknesses in the physical implementation of the system.
So instead of trying to break down the quantum fortress head-on, they're looking for cracks in the walls or back doors. I see, it's a more subtle approach. Can you give us an example of what a side-channel attack might look like?
Sure. Imagine an attacker trying to analyze the timing or power consumption of a quantum cryptography device. By doing that, they might be able to gain information about the secret key without actually breaking the encryption itself.
It's like they're listening for the creaking of door hinges or watching for flickering lights to figure out what's going on inside the fortress. It sounds like even with the power of quantum mechanics on our side, traditional security practices are still essential.
Absolutely. We can't think of quantum cryptography as a silver bullet that solves all our security problems. It's an incredibly powerful tool, but it's just one piece of the puzzle.
Right, it's about augmenting our existing security infrastructure with these new quantum tools to create a more robust, multi-layered security strategy.
Exactly. And it's important to remember that quantum cryptography, at least in its current form, mainly focuses on key distribution. It doesn't directly address other critical aspects of cryptography, like authentication or data integrity. So a comprehensive approach to security is still essential, even in the quantum age.
As we wrap up our deep dive into quantum cryptography, I'm really curious to hear your thoughts on the future of this field.
Well, I think it's safe to say that we're at a turning point. Quantum cryptography has the potential to revolutionize how we protect information, but it's still early days. As quantum technology continues to mature, we can expect to see more practical and affordable solutions emerge, which will open the doors to wider adoption across many different sectors.
So increased accessibility and usability will be key drivers for more applications. What other exciting developments are on the horizon?
Well, there's a lot of exciting research happening right now. For example, scientists are working on things like quantum repeaters, which could significantly extend the range of quantum communication.
Quantum repeaters.
Mm,
So those would act like booster stations for our quantum messengers, allowing them to travel much further without losing their signal.
you got it. Quantum repeaters are essential for establishing long-distance quantum communication networks, which would pave the way for secure communication on a global scale.
It's incredible to imagine a future where our internet, our financial systems, and even our entire digital infrastructure could be protected by these quantum shields.
It is, and it's not just about QKD. Remember those other protocols we talked about? Entanglement-based cryptography, quantum secret sharing, and quantum secure direct communication? All of these are rapidly evolving too. We can anticipate even more sophisticated and versatile protocols emerging, addressing a wider range of security needs as this field progresses.
It's like a symphony of quantum innovations, all working together to create a more secure digital world. Expert speaker, thank you so much for guiding us through this incredibly fascinating realm of quantum cryptography.
It's been my pleasure.
And to our listeners, we hope this deep dive has sparked your curiosity and left you wanting to learn more. The quantum world is full of surprises, and who knows what groundbreaking discoveries await us in the future. Until next time, keep exploring, keep asking questions, and keep diving deep.